Hello. This video is going to be discussing weak collision resistance, sometimes also called second pre-image resistance. All right, so we can go ahead and start with, discussion of weak collisions or second pre-image attacks. So a weak collision is where we have, let's say we are given a specific message, and we'll call it M1. Okay, we are given M1. What we need to do is find another message. We'll call it, M2, such that, such that the two hashes are equal to each other. So what this means is, remember back to strong collision resistance, we could find any two old messages that were, who hashed to the same value, whose hash was equal. In this case, we're given M1. And we have to find an M2 with a matching hash. Okay, so as you can imagine, this is a little more difficult here. It's a more difficult task to find this. Now, an example of second pre-image attack or weak collision attack is maybe, but there are a few. This can be used in a few different scenarios. But let's say I'm a developer and I have some code here, lines of code. And I'm a malicious developer only, let's say, I don't know, something like, SourceForge or let's say the Apple Store, doesn't know this. So I go ahead and submit this code for them to review. They okay it, right? They okay it. They okay putting it in the Apple Store. Okay. Now, how they may verify this code is they'll take a hash, of the code. And what I can do then, I can have, let's say I have some malicious code here. And this is my malicious code here. I can go ahead and submit this to the Apple Store. And since my hash of the malicious code equals a hash of the real code, Apple may say, oh, okay, yep, this is the code. Here it is. It's in the repository. Anybody can buy it. Anybody can download it. So in this way, I've distributed my malicious code. And that's just one example. We could also maybe, forge certificates if we find two certificates hashed to the same value and trick, a certifying authority into go ahead and, signing it digitally. So that's an example of a weak collision attack or of a second pre-image attack here. All right, and so now we'll get a little bit into the kind of the probability aspect here. So let's say what we're going to do is assume that we have, again, we're going to keep manageable numbers. We'll have a hash function that has a 32-bit output. Of course, this allows for 2 to 32nd hashes, right? 2 to 32nd outputs. So with this in mind, what's our probability? Let's say we want to calculate the probability. We'll scoot over a little bit here. So the probability of just some let's say we're given a hash. Let's say the probability of any old, a single generation of a hash, hitting the jackpot here of matching, a hash that we're given. Remember, we don't know, hashes they are deterministic in that there's, a given input will given, but you can't tell in advance what the output will be. That's, one of the properties of a hash. So the probability of a single generated hash randomly matching any old hash that we're given is going to be what? Should be easy, right? 1 over our universe, possible universe output space of hashes. So in this case, 1 over 2 to the 32nd, and we can kind of generalize this if we want, say 1 over 2 to the n. Right, for hashes. So that's the probability of a single hash, and that's pretty low here. Let's see. This is going to be, well, it's 1 over 4 billion. Up in, let's see, 1 over 2 to the 32nd. Yeah, so that's pretty small, times 100. So we are at, holy cow, 0.0000002% probability for a single attempt. This, you'll agree here, I'm pretty sure, this tells us that our probability of not getting a collision on a single hash generation, random, is going to be, remember back to our coin flipping problem, 1 minus, we can just flip the probability, 1 minus 1 over 2 to the 32nd, or 2 to the n if we want to generalize. And that's a pretty darn big probability. So we'll just subtract this by 1 and flip the sign. So there's a 99.999997% chance that we can't, randomly generate a hash that matches, any single hash. Okay, so let's say, how about if we, if we try x times just some number x? How about if we try, a whole bunch of times? Well, this is a little bit different than strong hashes. Think back to the strong hash, we had the birthday paradox. Here we don't. Remember, we're not tabulating a list. We're not saying, hey, I just want to find any hash that matches any other hash I've done so far. We want to match this particular hash. Let's say, H1. Let's say we're given H1. We want some hash. We want to find some hash. Call it, H, I don't know, Z. Sorry, let me redo this. We want to find some hash, H, Z, hash of some random message such that, H1 is equal to HZ. Here, let me write this with my stylus and my tablet here. It'll be a little neater instead of clicking away with the mouse. There we go. Okay, so we're not decreasing. Like I said, we're not decreasing our set size with each new try. So we can just go ahead and say our probability of not generating a collision after x, after non-x hash generation, is going to be, remember back to our coin flipping problem, we just multiply the probabilities, right? So if our probability remains this, since we don't reduce our set size each time, we're pretty much looking at 1 minus 1 over 2 to the 32nd to the x, right, where x is our number of tries. That should make sense to us. Okay? So that way our probability will get lower each time, which means that our probability of yes generating a hash after x tries is going to get higher each time, right? Remember, we can flip these again. And in our case of, a 32-bit output hash, our probability of yes generating after x tries would be 1 minus, the number we had earlier, 1 minus the non-probability, 1 minus 1 over 32nd to the x. Okay, and we can, let's take an example here. Earlier we talked about, we'll use the same example we did for the strong collision resistance. Earlier we kind of took the example of 2 to the 16th. Let's say we could feasibly compute 65,536 hashes. And I think that with strong collision resistance gave us, if I'm not mistaken, it gave us about a 39% chance of, generating a collision. So here we can, for weak collisions, we can say, all right, the probability of generating collision after 2 to the 16th hash attempts, random hash attempts, is 1 minus 1 over 2 to the 32nd, since that's our possible hash output size, to the 2 to the 16th, since x is going to be our number of tries. All right, so then we should have, for our probability of generating a collision in 2 to the 16th tries on a 32-bit hash, should be 1 minus 1 over 2 to the 32nd to the 2 to the 6. Oh, sorry. I did something wrong here. Okay, 1 minus 1 over 2 to the second to the 2 to the 16th. Oh, to the 16th. Yeah, something. Let me try this one more time, then I'll go to Wolfram if not, but I think I'm clicking something wrong here. 1 over 2 to the 32nd. There we go, to the 2 to the 16th. One minus, it's becoming a comedy of errors here. 32nd to the, okay, let me go to Wolfram. And here we have 1 minus 1 over 2 to the 32nd. Right, to the 2 to the 16th. Yeah, okay, so that's a pretty small number. 5, so that looks like 0.0015% chance, right, after 2 to the 16th try. So let me go back up here and we'll update. 0.00, what did I say, 0.0015? 0.00. I moved this over 2 decimal places, 0.0015, excuse me. So that's a big difference, 0.0015%. So we can see that it's a lot harder to generate, a weak collision over a strong collision. All right, and we can, let's say here, this can be interesting. Now this is set up for us to solve for our probability. So let's say we want to find at what point a collision is likely, let's say with this same 32-bit hash output. So we have here our probability of non-generation. So what I want is to get my probability about equal to 0.5, right? That's about the place that we're going to be likely to see a collision. So I can solve for x. Let's say 1 minus 1 over 2 to the 32nd to the x equals 0.5, right? Because my probability is 0.5. That's about when we have a collision, or about when we're probably, rather, going to have a collision. And you see this is kind of ripe for a logarithm problem. All right, remember back to logarithms, if we say an easy example is 2 cubed equals 8, remember the corresponding log is log base 2, 8 equals 3. So this means, remember the change of base formula. Also, this is going to be handy here. Remember change of base. Most calculators will only have log base 10 or log base e, natural log. For our change of base formula, we can simply say log of our answer over log of our base. And this way, it doesn't matter what the new log's base is. Okay, that's our change of base formula. So then, with that in mind, we can say log, okay, so log 2 cubed equals 8. Here we see that our base is at the bottom, so log 1 minus 1 over 2 to the 32nd. 8, which is our answer, 0.5, equals our exponent, which is our unknown here, x. Good. All right, so we've got this problem to where it should be rather easily solvable. Let's make sure. Okay, remember our change of base formula. Since we don't have a log, we don't conveniently have any way of calculating directly with 1 minus 1 over 2 to the 32nd as a base. We can use our change of base formula and say log 0.5 over log 1 minus 1 over 2 to the 32nd equals x. All right. So let's go ahead and do it. Let's have at it. Let's see how many hashes it would probably need to break a 32-bit hash function. Log 0.5 divided by log. Mathematica is pretty good at parsing this and knowing what I mean when I'm telling it. I don't know Mathematica. I don't know the exact syntax here, but it will probably guess correctly. If not, I'll readjust. Yep, there we go. How about that? Log 0.5 over log 1 minus 1 over 2 to the 32nd. The answer is, let's see here. Okay, so 2.97704, that's going to be 2,977,000,000, blah, blah, blah. Because if you look at this, let's go to calc. You see what it's telling us, 2,977,004. The rest is kind of inconsequential since we're talking about such big numbers. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9. Let me see. 1, 2, 3, 4, 5, 6, 7. Yeah, so this is 2,977,000,000, 40,000, whatever. So that's how many tries we would need to break this hash. And now look at this. 2 to the 32nd gives us our, our total hash output space. 2 to the 32nd is a little over 4 billion. So we're coming pretty close to having to exhaust our output space. Let's see. So if I divide this by 2 to the 32nd, multiplied by 100. Okay, so I'm exhausting. I'm having to exhaust about 69, ooh, darn, 69.31% my whole hash output space in order to, kind of be not guaranteed, but, have it likely that I'm able to generate a collision. And 69.31%, so, we're coming close. Now you see why a lot of authors will put in their, in the text that in order to break, a weak collision, we'll need on the order of 2 to the n tries. We go back here. Let me see, times, what was our number? If I multiply it, we'll get our number again. 2 to the 32nd divided by 100. There we go. So our original number was, 2,977,000,000. Okay. I can tell you what this exponent n will need to be here. Remember, oops, darn. So remember our little 2 cubed equals 8 example here. So we can say what? 2 to the what equals 2,977,040,000. And this will be the same. It should be a 0, and that should be a 0. So this will be the same as log 2,977,040,000. And that's basically, if we want to do a change of base here, we can say log 2,977,040,000 over log 2. And that'll give us probably close to 32, right? Should anyways. Okay. Actually, I had it up on the screen. I didn't need to delete it there. But anyways, so 2,977,040,000. Take the log of it and divide by the log of 2. There we go, 31.47. So this will take 2 to the 31.47 tries to, have a likelihood of breaking this hash. And that's pretty close, right, to being 2 to the n or 2 to the 32nd, where n is 32. So now you see why, it's kind of posited in a lot of text that it's going to take about on the order of 2 to the n to break a weak, to generate a weak collision, to break the hash that way. Feasibility, I don't know. What's feasible depends. We can have a whole lot of speculation here as to feasibility. It really depends on, what current CPU architecture tells us. We can kind of maybe, when planning a hash, we can extrapolate for, and account for Moore's law maybe in the future to see how long this hash may be valid. We have cloud computing and supercomputing also, which can kind of pool resources to, put a lot of computation into breaking a hash. So, feasibility discussion isn't something we can, is definitely outside of the scope of this, but anyways, you see the general idea here, and you've got the math behind it. Okay, I hope this helped.